In this video, I'm going to talk about the non-degenerate perturbation theory, which is 7.1 on the textbook. So before we begin, it's very important for us to define what perturbation really means. And one analogy I thought of that was interesting and intuitive is the following. So imagine you have, I'm going to use red pen here. You have this. And what is this? This is a soup. And we're going to call this soup a non-soup, which is a soup that you're given, right? So this is the soup that you have right now. And you taste the soup a little bit, and you realize that the soup is missing a little bit of salt. It's not salty enough. Then by that logic, we can define another soup, which I'm going to use the black pen to draw. It's the exact same as the original drawing by a different color, just to differentiate. This is gonna call the desired soup. So what does the soup mean? The soup means is exactly how you wanted it. It's a little bit saltier than the non-soup. Then mathematically, to formulate it, this whole process, what you could do is that you could draw the non-soup. So this is this is the desired soup. Is equal to your non-soup plus salt, right? And this salt, another name we're going to give is so-called correction. So this is what perturbation is about. It's about having these already known solution, in this case the known soup, making these tiny little adjustment here, which is adding the salt or adding the correction into it to obtain the desired perturbated sort of solution for the perturbated system. So in other word, this desired soup has another name, which is, in this case, it in the analogy, it corresponds to the perturbated case. This is the unperturbated case. And for unperturbated case, this is already known, right? So in quantum mechanics, this will correspond to a unperturbated system, which we have already solved the solution for. And then we're trying to obtain the solution for a perturbated case, which is a different case. So the way we can obtain that perturbated case, in this case, obtain that desired soup, is that we can make these tiny little adjustment or correction to our already known unperturbated case. So we obtain our perturbated case, which is our desired soup, right? And this way is much easier because we already know the solution, or already the case, we already know about this. We already have the soup known already, right? So it's much easier if you make correction based on what you know, instead of making an entire new soup based on scratch for this desired soup, right? So that is precisely what perturbation theory is about, is this procedure of obtaining approximating solution to perturbate the problem by building on the known exact solution of unperturbated case, right? So that's what we're trying to do here. And the unperturbated case will refer to the known soup, and the perturbated case will refer to the desired soup. But it might enough talking about all these soup stuff, and it's time for us to get into the mathematics of this, which is not that complicated. But so now we're gonna first look at our unperturbated soup, which is a system which is a Schrodinger equation that has already been solved for some potential, which we're gonna write as H0 psi n0 is equal to En0 psi n0. So this would stand for the unperturbated system, in this case the known soup. And this system has a initially non-Hamiltonian H0, has a corresponding eigenfunction psi n0 and eigenvalue En0, which satisfies this equation. And of course, for any eigenfunction like this, we know that it is going to form a off-normal basis, which are the following: psi n0 psi m0 is equal to delta mm. And the lambda, the delta here stands for the Kronecker delta, which is defined by is equal to 1 if n is equal to m, is equal to 0 if n is not equal to m, right? So this is just some stuff that you have learned in earlier quantum mechanics. So different quantum states are orthogonal to each other. So if you know, it's equal to, right, this equating to 0 ensures that different quantum states for n not equal to m, that they're orthogonal to each other, and if they're the same thing, then you just get psi 0 is equal to 1, right? This is what you get if n is equal to m, then this would just be the normalization or the wave function times its own composite conjugate, which is just going to be 1. So it's very intuitive. So we're just putting down some definition here. But here comes the interesting part, which is the part where we're going to introduce the perturbation. So now we perturbate the potential slightly, and we would like to find the new eigenfunction and eigenvalue, which are the following. H psi n is equal to E n psi n. So in this case, this will correspond to our desired soup that we want to find. And this equation right here would be equal to this, and then this would just be the perturbated or the desired soup in this case that we want to find. And the way we can find that is if we can build on our known solution to this and make correction on top of that. So we can begin the correction process by looking at the Hamiltonian. So the Hamiltonian, this is going to be equal to H0, which is the unperturbated Hamiltonian, plus lambda times H prime. So H0 is going to be the unperturbated Hamiltonian, which we already know how to solve. H prime here is going to be the perturbation, which is this small alternation or additional potential that slightly modify the system. And the lambda we're going to have here is this parameter that keeps track of exactly how much the perturbation contribute. And we can approximate our Hamiltonian to be this way. So this will be exactly the same as the example I've provided up here, where the Hamiltonian H here will be the desired soup you want to find, and you build on top of your known Hamiltonian, which is H0, and then you have your salt or correction, which is what this term is all about. So that's what's happening here. So you can write the same thing for psi n and En. So we can do a series. We can write them as power series in terms of lambda. So psi n. So we're just doing the same thing to psi n. So psi n we're gonna expand it to psi n 0 plus lambda psi n 1 plus lambda square psi n 2 blah 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 blah. For En it's gonna be the same thing. En 0 plus psi En 1 plus lambda square sine, oh no, sine En square, and blah 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 blah. So you can write this sort of same as, right, like same as what we have here, sort of, that you write this in terms of its multiple correction, right? So En here for our perturbated system would be consist of the original term from the unperturbated system plus all these tiny little bit of correction as you go, right? And each of these correspond as these terms expand right here, it goes into higher and higher orders of approximation. It's sort of like Taylor series, if you have learned that in calculus. It follows a sort of follow the same logic, right? It's about making these tiny little correction to match your desired perturbated system. And looking back at our example of the soup, it's the same thing. So this is the desired soup, perturbated is equal to your unperturbated plus correction and correction, right? And in this case, the higher order of correction will correspond to even more process of adding more salt, adding more salt or adding minor correction to make the result even more precise. So that's what's going on here. So now, since we have written we have an expression for each one of these terms in our equation. Then our h h psi n is equal to en psi n. So we can then just express them in terms of these expression, right? These power series. So this is going to be h0 plus lambda h prime times psi n 0 plus lambda psi n 1 plus lambda squared psi n 2 psi n squared, and keep going, is equal to en okay, I might even make the writing smaller here for it to fit. So I'm just gonna make it the writing so it's smaller, times the same thing so this is the formula we're gonna have, and we can further simplify this. So we can first look at the left side, right? So for the left side, let's copy and paste here. So for the left hand side, you're just gonna do the algebra, right? You're gonna multiply the first term by the second term by the third, and you do the same thing for the second, multiply, right? So it's just the algebra. So if you end up doing this, what you are going to obtain is the following: h0 psi n0 plus lambda h0 psi n1 plus h prime psi n0 plus lambda square h0 psi n square plus h prime psi n1 plus, and blah blah blah, it goes on. I keep making my writing a little bit too big. I just need to make this a little bit smaller. It's not working, but the idea is that this is gonna be equal to psi 1n plus blah blah blah. The term goes on for higher and higher lambda, right? So that's the idea of what you have on the left hand side. And if you follow the same logic on the right hand side for this, right, you're gonna obtain en. So right hand side is equal to. So if you expand following the same logic, this is what you're gonna get: plus lambda plus E1 and psi 1 plus E2 and psi 0 plus and blah, 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 blah. So it follows the same logic of how we obtain this expression, right? You just multiply each term by each term, you collect the like terms, in this case the lambdas, and then you can simplify them into this. So once we have this, the lowest order, or the unperturbated case, would be just h0 psi n0 plus en0 psi n0, right? So this is the lowest order. So lowest order, in this case, the lowest order will just be no correction, right? So it'll be a very rough and incorrect estimate. So this is just going to be equal to en0 psi n0. So, and the first order of correction you're gonna make, it's gonna be what? It's going to be h0, which is this whole term right here. This is the first correction. Psi n1 plus h prime psi n0 is equal to the term in here, which is en0 psi n1 plus en1 psi n0. So this is going to be the first order and the second order for the same logic, right? So what's going to be the second order is what's going to be inside the bracket for lambda squared. So it's going to be h0 psi square n plus h prime psi n1 is equal to e n0 psi square n plus e1n psi n1 plus en square psi n0. So what we're really doing here is that you can see that we're just defining the correction we're making. The lowest correction you'll be making, so in the soup analogy, what's the lowest correction you can make? The lowest correction you can make is not making any correction, which is basically having your desire equal to your known, which is a very wrong, it'll be a not close enough approximation. It wouldn't even be an approximation because you didn't really approximate, right? So it will be not, it will be saying your desired soup is equal to your known soup, but that is not the case because you want your desired soup to be a little bit more saltier than your known soup. So your known soup is going to come pretty close, but it's not the desired soup. Then you introduce the first sort of correction you make, and you make that correction, and let's say you find it to be a little, you find it still to be a little bit less salty, then you add a second batch of correction or a second batch of salt to make it even closer to what you want to desire. So in that case, each of these terms will correspond to your first order, second order, and third order. You can keep on going to this list as you get closer and closer to your desired soup. And your lowest order in this case would be the your soup that hasn't changed yet, right? Your known soup would be what you have for the lowest order, and for the first order will be the first correction you make. Second order will be the second correction you make. And you might be wondering why. In this first order and the second order, I'm no longer looking at lambda or lambda square for second order, or lambda, or for the third order, I would not be including lambda q. So I'm going to give you 5 seconds and think about why that is the case. The reason is very simple. Because we're solving order by order, right? We factor out each power of lambda and treat it as a separate equation. So once we isolate each order, the factor of lambda is no longer relevant because each equation now stands alone. Do you get what I'm saying? Is that you have your function here for the perturbated system, right? And then you have multiple magnitude of correction you build on the top of a non-perturbated system. Then if you look at each order of correction by itself, then it does not matter when you're solving that equation how much that sort of part contribute to the whole equation, because you already isolated each order, right? So the factor of lambda is no longer relevant because you isolate each order. You're only looking at how, let's say you're solving for the first order, you're looking at how the first order impacts the whole system, or you're only solving for the second order, right? Then once you sort of isolate each one of them, then how much each contribute to the total system is not relevant to you actually solving the system itself. And you can let that sink in a little bit, and I believe you'll understand why that is. And this is just going to be my first video for the general formulation part of this very long series of videos which I'm going to do. So in my next video, I'm going to 7.1.2, which is the first order theory, and I'll see you guys in the next video.